for completeness, I want to put together some videos for class 4, maybe re-record a couple topics that I had made previous semester's videos. But all right, so we're continuing on the 4th class of the semester and the 4th class of kinematics of particles. And here we're going to introduce coordinate transformations, and we're going to introduce path coordinates. So I think I'll talk about path coordinates first. Yeah, and one thing about the coordinate transformation, this is not covered in Johnston, but a book by Benson Tung. He is where I previously used it in another dynamics book, but we switched to Johnston a couple years ago. But I think coordinate transformation is a really good thing to learn how to do. And it helps you also with when you're doing computer programming of maybe trying to account for the orientation, changing orientation and things. It would be useful to learn how to code it in like MATLAB. Works out well because you can make like a matrices. Everybody loves matrices. Anyway, we're going to do that, and then tangential and normal components, aka path coordinates. And right here from the equation sheet is the velocity vector in path coordinates. It's very boring. It's just the speed times this unit vector. And we'll see that here in a second. And the acceleration, it's got 2 parts, and it's got the acceleration in tangential direction, which is actually a change in speed, and the acceleration in the normal direction, which you could see over here is the ever so popular centrifugal acceleration. And here you see new dogs driving off the cliff right there. So here are 2 coordinate systems. This is the one we're doing today, and then in the next class we're going to do radial and transverse, which we also call polar coordinates. And they're similar in some ways, but there's also some differences. So what are the differences? Well, in the path coordinates, our coordinate system goes along for the ride with the particle. It's translated, it's moving with the particle. Now, it doesn't have to be attached to the particle, but its orientation is decided by the particle on the path, because the tangential coordinate, this unit vector ET, tangential, is always tangent to the path, just like velocity. And the normal coordinate is always perpendicular to that, but also always points to the center of curvature, right? That just happens to, I mean, you could think by the consequence of that is the perpendicular to the tangent is something that points to the center of curvature of the path, right? But with polar coordinates, the origin is a fixed point. Now, it doesn't have to be a fixed point. It could be moving, but then we would have to do some relative motion as well. So just let you know that it's there can be more complicated things where, like, maybe if a disk was like spinning, what was translating through the air, but we wanted to know something on what's happening onto the disk, and we wanted to know what's actually happening relative to like some other frame of reference. Yes, the thing could move, right? But that's a more complicated situation. As a general statement, the origin is some fixed known point, and all the coordinate systems are based on where the particle is with respect to that fixed point. So the big tangents that we could go, just to repeat here, is that the big differences between the path and the polar is that the coordinate system is moving along with the particle, whereas the polar origin is fixed at a point, but its coordinate system follows the particle from a distance, right? So we have these 2 cartoons that I put together, and some of these were some of the first cartoons that I drew of a new dog. In fact, these are early versions. And the path coordinate system, what the important thing to note here is that you have to turn to stay on the path, right? So like if you just keep going, if you're at one point tangent to the path, but then you leave the path right there, you will keep, if you stop like making a turn, you will just go off the cliff right there, right? So it also, when we get here to a second, I will point out that the centrifugal acceleration, this is the big idea, the big concept of centrifugal acceleration, that like you have to accelerate towards the center of the curvature in order to stay on the path, if that makes sense. And I'll do the mental gymnastics of that, and hopefully that will stick with you, especially with respect to the cartoon. You can think about driving off of the cliff as being a consequence of not having centrifugal acceleration. And then in polar coordinates, we will talk about in the next class, but we have this radial motion as well as a spinning motion, right? So we're describing the motion by two fundamental parameters: the length of the distance from the origin to the point, and the angular orientation of that vector that points toward the point. And so we can have velocity in that respect, and also acceleration in that respect. And so I show Newt Dog on a chair, stool spinning, right, where the fishing line and how fast or slow and it pans out is the radial direction, whereas where he's spinning determines the angular position, right? So there's these two parameters that we're using fundamentally to describe the motion, which is, once again, that's kinematics, right? It's describing the motion. So here's two different ways, and all of these are interchangeable. All right, so we ask what's the same in them. The main thing that's the same or similar to them is that these orientations of the unit vectors change with time. Right, so if you remember back in class 3, we made a big deal out of taking the derivative of vectors, and this is the reason why. Because when we take the derivative of a vector, we also have to take the derivative of the magnitude and its unit vector. So if the unit vector is changing with time, we have to account for that. All right, so in doing that, all right, so this is really just so that's the big introduction for today's discussion. Because we have multiple coordinate systems, we should want to know how can we systematically move from one coordinate system to another. Now, generally, I would have done this before I actually taught out of Benson Tung's book. I usually just made a bunch of sketches and figured out where the vector broke vectors into components depending on what the coordinate system was, and then worked out what the angles were. But here's more of a systematic approach, and I think it's a really useful thing. So it boggles the mind maybe a little bit at first, but you'll get a hang of it. Okay, so I'm saying this is a textbook supplement here, because I'm adding this stuff in here. So let's say we have two coordinate systems, right? One is going to be the IJ, we're used to that, and another new coordinate system we're just going to call B1 and B2, right? And so these are unit vectors. I think I probably would have stuck with the little E notation personally, but that's okay. So what we could do here, if we had, I'll just take B, right? We could break B1 down into terms of I and J. So if we did that right there, we would have cosine of I and the cosine of theta I, and then the sine of theta J would need to be, and remember, B is a unit vector, so its magnitude is 1, right? So we don't need to actually necessarily multiply it by the front of those to figure out that here is now B1 represented as in terms of I and J, right there. Okay, so if we were going to take B2 right there instead, all right, so B2, let's draw him over to the side. I wish I had drawn him over to the side here. If we drew him over to the side now, here's B2, we would see that we would have this and that right there, right? And the angle is right here, which has to be the same as that angle right there, right? Sure. Here's the magnitude B2, so we'd say that this is going to be I don't like drawing negatives and arrows next to each other because that arrow means that it's negative. But we could say that in the I direction, we have a negative sine of theta I, and in the j direction, we have a positive cosine of theta because it's adjacent right here, and it is going positive, right? J, right? So what we could do is we could take that and we could put it into like a little matrix form right here, or we call this a transformation array, where we go cosine of theta and sine of theta, negative sine of theta, and cosine of theta. And this array will often, this is not universal, simply not universal. We have to create this array depending on our orientation. This will happen a lot, so this will be one that we use, but there could be other different scenarios where we come out, especially since that we have now we have two different now we have three coordinate systems. We have three different coordinate systems that we've learned. I don't know what happened there. Okay, we have rectangular, we have path coordinates, and then we have polar coordinates. So we might want to jump back and forth between those. So this is our motivation to do that. So like we could have like coordinate systems that are like that right there, right? And then maybe we want to get it into I and J right there, right? So if this was like, if the path were like something like that, right? So I'm trying to draw, I'm not doing a good job. If I'm trying to draw like a path that might exist right there. So a path that might exist, and that's tangent to it right there, right? So here's the particle, and here's my ET, and here's my EN are right there. Let's say that this is the angle right there, right? So looking at that right there, we would say, well, that means that this is the same angle right there, right? And if you're ever confused by it, here's what I do. If I know that angle, I think, and I like turn it there and I close this angle. So I'm sweeping this over to get up to line up with J, and you notice that that's going to be the same angle of that sweeping up right there, right? So like you use a little L will help you try to figure that out. So this array that we will draw as part of this thing, let's see, I'm going to do that correctly, and let's go like this. Put them up there. And by the way, it depends on which way, when you're making this array, you can go backwards with it, but I'm going to go ahead and make it I and J right here, and make this ET and EN. You don't have to have them. We could put the I and the J here and the ET and the EN up there. It doesn't matter. Just as long as you use it correctly, and we'll show you how to use it here in an example in the next one. It's much easier to see it in an example and to practice doing this. But if you have ET, you'll see that that's going into the negative, and that's the this ends up being cosine, right? Negative cosine of theta, right? Because it's in the negative I direction, that T. We could also see that it's going to be in the negative sine, right, of J, right? Because its component in the J direction is going downwards. That's a negative sine of theta. If we take the EN now, it's in terms of I. That too is a negative, but now it's the sine, right, of theta. And then we see it's the for the J, it's the cosine because it's adjacent, but it's positive. So you'll notice the pattern that happens here. For one thing, it's almost symmetric. It's almost symmetric, except this is negative where that one isn't. And you could also have it where this is the sine, and this is the sine, and this is the cosine, and this is the cosine. But one of them will be negative, or one of them will be positive, I should say. One of them will be a different sign than the other three. Always, right? So, but this is going to be the transformation array, and so to see it in action is to really understand it. So, I don't know. How long is the video right now? Do I want to make this into a different video length? This is 14 minutes. Let me go to a different video to show you the thing in action.